Welcome to Institute Seminar Days 2024, and the chair of the first session is Sayantan. So we have 10-minute talks, and since the schedule is packed, it's very important to try to stick to schedule. And those of you who are giving talks in the following sessions, please send your slides as quickly as possible to media@imsc.res.in so that there's no time wasted during changeovers from one talk to the other. The chair of the first session is Sayantan, so I'll hand it over to him.
Thanks very much, Amrief. And so we can just get started. So our first talk is by our colleague Srihari, who will tell us about baryogenesis. And it's a blackboard talk, so we will have a very informal discussions on it. Please, Srihari.
Okay, good morning everybody. So thanks to the organizers for putting this together. My challenge would be to stick to the time. I'll try my best. So there's a lot of preliminary things I felt I should say. I'll start with that, hopefully quickly, and then get to what is the crux of baryogenesis. So, and also if my writing gets too small and it's not visible from the back, please let me know. So I'll try to consciously keep it a bit bigger. Baryogenesis. So what is baryogenesis? So baryo stands for baryon, and genesis is how did it come about, or origin. So we want to learn about the origin of baryons. And where is the setting? It is the universe. So we want to learn about the origin of baryons in the universe. So universe is everything that we see around us. So we are in fact made of baryons. And a distinction that I would like you to keep in mind is we are made of baryons but not antibaryons. So that's a crucial thing in baryogenesis. So the question is, how is it that everything that we see around us is all baryons, but there are no antibaryons? So I'll say a little bit more about it, but that's a crucial question we wish to answer. So what are these baryons? So I told you we are made of baryons. So these are, let's say, the proton, neutron, and there are a bunch of other baryons. But for our purposes here, we'll just stick to these. These are the stable baryons. In fact, the neutron is also not stable. If it's a free neutron, it will decay. So really the only stable baryon is the proton. And mostly we are made up of protons and neutrons in the nucleus. So everything we see around us is put together by protons and neutrons. And of course, we also have electrons, which is not a baryon. But for charge neutrality of objects around us, there are equal number of protons and electrons in the universe, we think. And there is no reason to suspect this. So if I can answer how many protons there are in the universe, automatically I will assume that there are the same number of electrons for charge neutrality of the entire universe. So I will not really keep track of electron. It is just equal to the number of protons. So neutron, the number is little bit lesser than the number of protons if I count in the universe. So this is a parenthetical remark. So I'll mostly not refer to the neutron, but they are around. So mainly we will keep track of protons. And in the universe, what else is there? We can have photons, right? Photon is a light particle, the particle of electromagnetism, light. So in the universe, we can observe photons. And we have neutrinos. But neutrinos are so weakly interacting that they're basically just sitting there, not interacting anything. They're decoupled. They're so weakly interacting that they don't do much. So for this talk, I'll forget about that. So mainly the players are the protons and the photons. So I want to ask how many protons are there in the universe that we see. And of course, because the universe is a temperature bath, so it's a bath in thermal equilibrium at early times. And so it is a gas of protons and photons. interacting thermally. So it's a thermal system. So the universe to us is then a box. I will consider one region of the universe. It's let's say a cube of some 1 meter by 1 meter by 1 meter. I look in this volume. And if I look at very early times, we think the universe, we are very sure that it began in what is termed as a Big Bang, a very hot temperature phase, right? And so this Big Bang, after the Big Bang, the universe just expands and cools. Whenever a gas expands, it cools. So this is at very high temperature, and we pick up the action when, let's say, the temperature is still incredibly high compared to our human temperature, something like 10 to the 16 Kelvin. So let's just say that the universe from, who knows, some incredibly high temperature eventually cooled to some temperature like 10 to the 16 Kelvin. And here, I want to keep track of protons and photons in this temperature bath, right? And so in particle physics or in special relativity, quantum mechanics, one of the basic principles is that whenever you have a particle, you also have its antiparticle. So we have antiprotons also necessarily in the framework, right? And in the lab, we routinely see that if I have a photon, it can split to proton-antiproton pair. That's something which we routinely see in the lab. Similarly, if I have a proton and an antiproton, they can annihilate each other to just give me light, photons. These processes are routine. We observe them, there is no doubt about this. But important point is whenever a photon splits, it will split to one proton and one antiproton, never a single proton, because that would violate charge. So it should always split to a proton-antiproton pair. So these are in thermal equilibrium in the early universe. So let me denote a proton by an open circle and an antiproton by a solid circle, right? So I don't know why they came out different size, but okay. So there are some number of protons and some number of antiprotons. And so that's and they are in equilibrium with a lot of photons, right? At some temperature T, so the number of photons is given. If I tell you what is the temperature, the number of photons is given by thermodynamics, basic thermodynamics. I can work out how many photons there are. So this is where we start at 10 to the 16 Kelvin, and then we ask, as the universe cools, it expands. So the present day universe has become bigger. This region expands. So it has cooled. And since this process can happen, proton and antiproton keeps annihilating, and at some point the reverse reaction becomes energetically unfavorable. So this shuts off while this keeps happening. So it depletes the number of protons and antiprotons. So these things will annihilate with each other to give you photons. So late time, there are many more photons, right? Because everything is annihilating to photons, incredibly large number of photons if we look in our present day universe. But there are a few protons and antiprotons. What are left over, right? So this is what you would expect. A gas of protons and antiprotons in equilibrium with photons expands and cools. And since there are annihilations of protons and antiprotons given by this, they should always annihilate pairs, right? So they get rid of each other in pairs. And you should be left with such a state now. But this is something that we have made observations of. We can look in our neighborhood, galaxies and so on. Oh, I should have changed the tune, but anyway. So when we make observations, remarkably, we find that there are no antiprotons. There is only this one left. And for charge neutrality, I told you there is somewhere one electron. If there is a proton, there is also some electron somewhere to make it charge neutral, right? So this is the universe that we observe. There are no antiprotons. And it's a big puzzle in particle physics. How, right? How did this come about? We would expect naively that there is an equal number of protons and antiprotons starting from a symmetric early universe. But we find that this is not symmetric. And if I look at the number of baryons, take the difference with number of antibaryons, divide it by the number of photons. This is this ratio which is termed as eta. This is an observation that has been made, and we find roughly this ratio is around 10 to the minus 9. So for every billion photons, we have about 1 proton in the large scale universe. So it's, what we are made of on Earth, it is a very highly concentrated, like place because of gravity. But if you average this over the entire universe, this is the number that we observe. Like for every billion photons, we have 1 proton that is left over. So the question is, how do you explain that in theory, right? I mean, this is observation. And so that is where we as particle physicists come in, and we try to ask, can we explain this kind of an observation? So you could try in any theory, if you have to explain this kind of a process, Shakarov in 1967 gave 3 conditions. In any theory, 3 conditions, he said, must be satisfied. Oh. So I think I better wind up. He gave 3 conditions. So one is baryon number must be violated in some process. Second condition, C and CP violation should be present. This just distinguishes particles and antiparticles. That must happen, otherwise you always end up with equal things, whatever you start with. The third thing he said is departure from thermal equilibrium. If the universe never deviates from thermal equilibrium, then whatever you produce, the reverse reaction will erase it. So Sakharov said these 3 conditions must be true in any theory. And our beloved theory is the standard model. We have tested it very well. So we can ask, in the standard model, are these 3 conditions there? And remarkably, yes, all of these 3 conditions are present in the standard model. And so people have gone and computed how much of baryon asymmetry will you find? Like, can we explain 10 to the minus 9? And the answer came out, no. It falls short by about 5 or 6 orders of magnitude, and that's the puzzle. And so my attempt has been to take theories beyond the standard model. For instance, I am looking at a new particle, which I would call chi, which decays to a baryon, but it is constructed to be a majoron or fermion, so it can decay also to an antibaryon. And if I can arrange in my theory that the decay rate of chi going to baryon is not equal to the decay rate of chi going to antibaryons. Again, I will implement these 3 conditions for that to happen. And the attempt is, can I explain this 10 to the minus 9? So that's my work in the last couple of years. Okay, I'll just stop there.
Thanks, Srihari, for setting the stage, and we have time for one question, if you want to ask.
So, why does one look into the non-equilibrium case here? Why does one look into the Shakarov's condition?
Yeah, so it is just that if I have some process, let's say chi goes to B, baryons, in thermal equilibrium there is also B goes to chi.
Yes.
If these 2 are in equilibrium, whatever baryon number that I produce will get erased by the inverse reaction.
So what about looking for the non-equilibrium steady state rather than the equilibrium state?
Non-equilibrium phases.
Steady state, in non-equilibrium steady state you can...
So one does, technically doing this, one solves the Boltzmann equation.
Okay.
So you deviate from thermal equilibrium, and then you ask what are the steady state values of the number densities. Yeah, technically that's how you would do the calculation. So that's what Sakharov is saying, you have to deviate from thermal equilibrium. Otherwise, inverse reaction will always erase.
Okay. You can take the questions during coffee time then, please. Yeah. So thanks, Srihari, again. And we hand over to Amri, who will tell us about representation of zeta functions.
So yeah, I'm going to talk about not representation of, but representation zeta functions. So so there's you must have seen some special cases of this kind of a thing. So suppose you have a sequence, then you can try to understand properties of the sequence by constructing a kind of generating function. So this is called a Dirichlet's this is called a Dirichlet generating function. So it's just your sequence is an, so you're trying to count something that's indexed by n maybe, and the Dirichlet zeta generating function is just an by n to the power s. So it's a function in this variable s, and these kind of functions, they have so it's an infinite sum, so you should ask whether it converges or not. And they have a behavior that there's a line in the complex plane to the right of which they converge, and that's called the abscissa of convergence. And it turns out that the growth of the sequence can be captured by this abscissa of convergence. So if the sequence grows polynomially with degree alpha, then the abscissa of convergence will be about alpha plus 1. So I mean, I guess you've all seen this probably. The Riemann zeta function is the primordial example of a Dirichlet generating function. It's just a sequence where all the terms are equal to 1. And the unique factorization of integers tells you that this zeta function has a factorization into what are called Euler factors. So this was discovered by Euler, and so it has a product decomposition over primes. This basically just comes from the fact that every integer has a unique factorization into prime numbers. And this one converges for a real part of S greater than 1, which is maybe an exercise in calculus when we study convergent series. Now I'm going to introduce something called a global field. I'll come back to that in a minute. So there are all these, but you can think of maybe the rational numbers. So if you have the rational numbers, there's a thing called the Dedekind zeta function, and this somehow captures some information about this field. So when you take this to be the field of rational numbers, this is just going to be the Riemann zeta function. But there are other fields that number theorists are interested in, such as the field of Gaussian integers. So you just take Gaussian numbers, you just take rational numbers a plus ib, you just take numbers of the form a plus ib where a and b are rational numbers. That's a field. And you may want fields where roots to certain equations are included. So you want to look at things bigger than the rational numbers, and those are examples of global fields. So the Dedekind zeta function of the field Q is just the usual Riemann zeta function, but there are some other kinds of fields which arise in algebraic geometry. So if you look at a finite field FQ, and then you can look at rational functions in one variable with coefficients in that field. Now that is interesting in algebraic geometry because it is the field of rational functions of the simplest algebraic curve, namely the projective line. So these are called function fields, and so you have algebraic extensions of Q, that is you take Q and enlarge it a bit to include roots of equations, and algebraic extensions of this FQT. These are what I mean by global fields. So they all have zeta functions, and this one is also very easy to compute. So if you try to compute the zeta function of FQT, so the zeta function has this thing that you must take a sum over all non-zero ideals in the ring of integers, so whatever that means. But here, so these are rational functions, so there's an analogy between rational numbers and between integers and polynomials. That analogy, if you take it, rational numbers correspond to rational functions, and this Riemann zeta function is related to counting, just counting integers, so to speak. This one is related to counting monic polynomials, and it ends up having a very nice and simple, it's actually much simpler than the Riemann zeta function, right? The Riemann zeta function is something much harder to understand, but this is very simple. It's just given by this very simple formula. But what is surprising here is that this converges again for S, real part of S greater than 1. So we see the same behavior of the zeta function whether you associate it to a number field or to a function field. And so in general it's known that the Dedekind zeta function of any global field has abscissa of convergence 1 and can be extended to a meromorphic function slightly to the left of that. So it will have poles to the left of that, but you can extend it slightly with poles, and beyond that we don't know what happens. So now you know, we are going to look at certain others. So I said, you know, this Riemann zeta function, Dedekind zeta functions, these are special cases. Yes, S is a complex number.
So it goes from C to C?
Well, it may not converge, so then, yeah, yeah. So, and then even if it doesn't converge, you can try to extend it by analytic continuation to a slightly larger region. So there's the region where it converges, and then you try to extend it. So, so now there's been some interesting developments that suppose you have a group G, then we try to realize this group in vector spaces, and a representation of a group is irreducible if you cannot find a subspace of that vector space which is invariant under the transformations in that group. And so those are irreducible representations, and counting irreducible representations of a given size tells you something about the group. So now the representation zeta function of this title is this zeta function where an is just the number of irreducible representations of G of dimension n. So you can just rewrite this as sum over all irreducible representations of whatever dimension 1 over dimension of rho s. And the problem that we have that we are working on is for an interesting group G, what is the abscissa of convergence of this zeta function? So I need to explain what is an interesting group. So there's this class of groups, most familiar groups that physicists work with and so on, they are actually locally compact groups. And these groups have a natural sort of notion of volume which is called the Haar measure. And a lattice inside a locally compact group is a subgroup that is discrete, so its points are separated from each other, and it has the quotient space has finite Haar measure. So a simple example you can think of is R squared, which is a group under addition, and Z squared is a lattice inside R squared, right, the integer points. Because they are sort of scattered all over, and a fundamental domain for the integer points in the real space is just a square, and that has finite volume. So that's what I mean by, you know, the quotient space has finite Haar measure with respect to the notion of volume that you have on the group G. And there's a deep theorem of Margulis which says that that lattices are basically something called arithmetic. So for a nice class of groups. So semi-simple Lie groups of rank greater than 2. So you can think of SLN where n is greater than or equal to 3. So if you look at SLN-R where n is greater than or equal to 3, then you have, this should be SLN inside SLN-R, n greater than or equal to 3, and this is sort of the number field case, and the function field case is SLN. So you just look at n by n matrices with determinant 1, but the entries are now polynomials, and you think of it as sitting inside this sort of weird group of whose entries are, that's another typo, Laurent series in the variable T inverse. So anyway, this is the important side to keep track of, SLN-Z and SLN of polynomials. So these are the groups for which we would be interested in understanding the representation zeta function and the abscissa of convergence. So, so there's a conjecture of Larsen and Lubotsky which says that if you have two irreducible lattices in a group of rank greater than 2, then the zeta functions must have the same abscissa of convergence, saying that, you know, different lattices will somehow still have the same rough behavior in terms of representation theory. And to approach this problem, one uses Margulis arithmeticity. You need to somehow get a grip on what these lattices are, and Margulis's arithmeticity theorem tells us that we can realize these groups as some sort of products of groups which I will come to in a moment, G of OS. So you have this field, you have this lattice, and so you have this lattice, and what you are going to show is that this group has some sort of product decomposition. Not important at this point, but understanding these factors is the key to proving the conjecture. So we need to understand these local zeta functions. So let me give you an example. So if you want to look at SLNZ, then the local group will be SLN of the p-adic integers. So these p-adic integers are some sort of compact completion of the integers, focusing on phenomena that happen at the prime p. And and you can also look at power series in a finite field. So these groups are sort of limiting cases of finite groups. SLNZP is this pointer is not working. Anyway, SLNZP is a limiting case of the groups of integers mod p to the power k, and SLN of the power series is a limiting case of polynomials mod t to the power k. So these are limiting cases of finite groups, and finally we need to understand the representation theory of these finite groups. So the main difficulty in this kind of work is that we may understand the representation theory of SLN over a finite field, but these rings, the representation theory is wild. So there are some technical conditions, field of characteristic 0, and the Larsen-Lubotsky conjecture was proved for groups of rank 2. So basically these are groups SL3, SU3, SL1 over a division algebra of rank 3 and SU1 of a division algebra. So this was proved using p-adic integration techniques in 2014, and they also proved it for all higher rank groups, but the operative word here is characteristic 0, which means the fields that come from rational numbers. 10 minutes up. Okay, so I have just one more slide, which is, so we have these two groups, SLN Z mod p to the kz and SLN fp mod t to the k. So these are different groups of the same order, but they are not isomorphic. Do they have the same class equations? That's not known, but for k equals 2, this was proved by Pooja in her PhD thesis. Do they have the same representation zeta functions? For n greater than 3, this is an open problem. So in recent work with Urion and Pooja Singla, we were able to show that these local factors, these two kinds of groups have the same representation zeta functions, and using that we were able to extend the proof of the Larsen-Lubotsky conjecture to groups of rank 2. So with positive characteristic. So
Thanks, Amri, for this nice talk. One question, please, when we change the slides. Have some question. Slide.
Okay, stunned.
Any question for Amri? Okay, if not, then let's thank Amri again. Then our next speaker is Vikas, and he will tell us about planar graphs, more about planar graphs. Please, Vikas.
So good morning, everyone. Today I'll be talking about the complexity of pair domination problem in AT free graphs and planar graphs. So this is a variant of well-studied problem in graph theory called domination in graphs. So let's first understand what is domination. Suppose we have a set of villages in some remote part of the country, and we want to build hospitals to provide medical facilities to the residents of the villages. Now, since building a hospital is very costly, so preferably we do not want to build hospitals in all the villages, but we want to pick some villages and we will build hospitals there. And we have a constraint that a person should not travel more than 10 kilometers to visit a hospital. Now, this problem can be modeled as a graph theoretic problem where each vertex will represent a village and two vertices are adjacent if the distance between the corresponding villages is at most 10 kilometers. Now, in this graph we are interested in finding a subset S of vertices such that if a vertex is not in S, it should be adjacent to a vertex in S. So, formally such a set is called dominating set, and formally a subset D of vertices in a graph is called dominating set if every vertex outside D has a neighbor in D. For example, in this graph, the vertices that are colored red forms a dominating set. This concept was introduced by Burge and Orr in 1962, formally introduced by Burge and Orr. Since if you take all the vertices of the graph, it will form a dominating set. So, we are interested in finding a minimum cardinality dominating set of a graph, which is called minimum domination problem, and the minimum cardinality of a dominating set is called domination number, which is denoted by this symbol gamma g. It has applications in computer communication networks, locating radar station problems and many more. The problem is well studied in the literature and over 4,000 articles are published till date. So, it has a lot of application and depending upon the applications, people have introduced generalizations and some variants of the domination. So, today I am going to talk about a variant of domination which is known as pair domination. So, in the previous example, these three vertices will dominate all the vertices of the graph. So, suppose we want to pair each of the vertex in the dominating set with another vertex of the dominating set, so that in case of emergency they can make some communication or they can act as a backup for each other. So, with this motivation, Heinz and Slater introduced a concept called pair domination. So, in a graph with no isolated vertices, a dominating set is called pair dominating set if the graph induced on D has a perfect matching, and a pair dominating exists if and only if the graph has no isolated vertices. For the graph that is here, the vertices that are colored green forms a pair dominating set. Similar to domination problem, here also we are interested in finding a minimum cardinality pair dominating set, which is known as minimum pair domination problem, and the minimum cardinality of a pair dominating set is known as pair domination number. So, several bounds have been established on the pair domination number. In 2009, Goddard and Henning conjectured that for a graph on n vertices where the minimum degree is at least 3, the pair domination number is at most 4/7 of the size of the vertex set, and some progress has been made on this conjecture. At the algorithmic front, the minimum pair domination problem on a graph with maximum degree delta can be approximated within the ratio of log of 2 delta plus 1, and it cannot be approximated within better than log of size of vertex set for any epsilon greater than 0 unless p equal to np. The problem is also known to be APX complete for the graphs with maximum degree 3. Since the problem is hard on the general graphs, people have considered special graph classes to study the complexity of the problem. So, for the graph classes that is represented above the dotted line, the problem is NP complete, and for the graph classes that is on the below the dotted line, the problem is polytime solvable. The complexity of the problem remains open for like almost 7 years before we solve the complexity of the problem on planar graphs, and we proved that it is NP complete for the planar graphs. We also gave a polynomial time algorithm for the problem on AT-free graphs and an approximation algorithm for the problem on AT-free graphs. So, these are the results that we gave. Like we also proved that for a given graph it is NP hard to decide if the pair domination number is exactly equal to the domination number. So, what is an asteroidal triple graph? In a graph, let X be the set of 3 independent vertices. This set S is called asteroidal triple if for any 2 vertices in the set there exists a path that avoids the neighborhood of the close neighborhood of the third. So that this set is called AT. For example, in this graph, the vertices that are colored red forms an AT. And a graph is AT free if it does not contain a asteroidal triple. So what is good about asteroidal triple graphs, AT free graphs, is that there exists a pair of vertices, special pair of vertices which is called dominating pair. And what is dominating pair? So a pair of vertices xy is called dominating pair. If you take any path connecting x and y, the vertex set of that path is a dominating set. And if you take the shortest path between these two vertices, that is called dominating shortest path. So in this example, V1 and V3 is a dominating pair, and the path V1, V2, V3 is a dominating shortest path. So using this dominating shortest path, we presented a 2.5 approximation algorithm for the problem on AT free graphs. There is a special property of this AT free graph that there exists for a like if G is an any AT free graph with dominating pair x and y, and T is a BFS tree of this graph G rooted at x, and L0, L1, L2 are the BFS levels of this BFS tree, then there exists a linear time algorithm that computes a path x0 to xd such that each xi lies in the level Li, and all the vertices at level Li is either adjacent to xi or xi minus 1. So using this property, we are able to bound the number of vertices from any j plus 1 conjugative BFS levels that are coming in a minimum pair dominating set. And that is, we proved that there exists a minimum cardinality pair dominating set dp such that dp contains at most j plus 4 vertices from any j plus 1 conjugative BFS levels. And using this property, we able to design a Pearl time algorithm. We also studied the complexity of the problem in planar graphs. We proved that the problem is NP complete on planar graphs, and for this purpose we describe a reduction from minimum vertex cover problem, which is known to be NP complete for cubic graphs. So we take a cubic graph and we replace each of the vertices by this gadget that is shown here, and we proved that in the constructed graph G prime, the pair domination number of G prime is equal to 4 times the size of the vertex set of G plus 2 times beta G, where beta G denotes the minimum vertex cover of the graph. It is known that the pair domination number is sandwiched between the domination number and 2 times the domination number. So Alvarado et al. In 2015 studied the equality of this inequation, and he proved that it is NP hard to decide for a given graph whether the pair domination number is equal to 2 times the domination number, and in the same paper he conjectured that it is NP hard to decide for a given graph whether the pair domination number is equal to domination number, and we settled this conjecture in affirmative answer. Thank you.
Thanks, Vikas, for sharing your research with us. Any questions for Vikas? I don't see any, so let's thank Vikas again. So next speaker is Soumyadeep, and he will tell us this exciting talk. Title look already exciting.
How do I change
Into
the
the eyes
slides?
of a biological cell.
This is the slide. No, this next slide. Okay. Okay.
Okay, please go ahead.
Yeah. Thank you, Shantanu. Good morning, everyone. First, I would like to thank the organizers for giving me the opportunity to speak and tell about my work. So basically, I work at the interface of physics and biology, and try to take in the physical principles and try to understand how biological systems work. And particularly work on signaling networks. I hope so. This is like a diverse audience is there. So everyone knows what a biological cell is, right? So we are all made up of those cells. And so basically my work is to kind of understand how these cells are able to kind of perceive their environment, take in the information, gather the information from the environment, and process it, and eventually like make decisions, important decisions, like whether to divide or not, or whether to differentiate, and so on. So before I just start, what is it changing? Why the slide is not changing? Yes.
Frozen or?
Yeah, so this video is not working. Is this video, can this video work? This one? Huh? Yeah. Or is it frozen? Yeah. This one, yeah. Yeah, just have a look at this video. Is it working? God. It's working here, but it's not showing. Anyways, yeah. So what I wanted to show was this video. It's a very famous video. This like. What you will expect to see from here is that this is actually a white blood cell. It's like it will be chasing a pathogen over here, and eventually like it's like it will track this pathogen, and eventually like at some point of time it will consume it. So I mean when we first you'll be looking at this this video, and you'll see that somewhere there's these cells have some eyes or something, but actually in reality they don't have these eyes like as we do. We can like see people and like follow them or whatever. So but cells they have a more rudimentary kind of mechanisms to kind of sense their environment. What they have eventually is these receptors, okay, and this what the receptors what they do is that they sense this chemical signals, right? I mean which can be any molecules or something like that, and when they let's say when a molecule kind of when any of the molecule like binds to these receptors, it triggers it like sends us information downstream. Okay, and inside the cell you will have these different other molecules would be there, okay, of different types, which are like the protein molecules, and they would be so once it gets the signal from the membrane, it kind of will transfer that information. It will activate some protein, okay, and that protein will again activate some other protein. In this way it will pass down the information downstream and to the nucleus, where let's say some proteins will be produced, right, and eventually like the cells would respond to that, right. And so it is very important to understand the network which is there, which is like the bridging this the outer, like the membrane to the inner nucleus, and because like any defects inside this like this network can lead to like a lot of pathological consequences it can have, like such as cancer and all. So, so a lot of important processing that the cells can do, okay, and one of the important processing that the cells can do is like be sensitive to any change in the chemical stimulus, okay, in the environment, right? And yeah, again it's not working. I don't know. I think it's frozen somewhere. হচ্ছে না এখানে হচ্ছে
Can you make it a PDF file?
Okay, I have a PDF. Yeah, just the PDF there. This.
Please don't use this Windows.
Which one? PDF I have. Where is Vasan? So I have sent this. Is that mail it? Yeah. I think last. Yesterday I sent yesterday.
Can you search it?
DIP. Yeah, this is. Yeah. Scanning soon.
Save it. Check it out.
Yeah, so I just like to compare this with how a camera works, like the sensitivity part. So suppose, I mean, most of you have some experience using a camera. So, so suppose you have an object and it's a very dull object, it's there, like not much you can get out of that object. And like now you want to, when you are taking the pictures, say, so you want your camera to be like very sensitive, I mean in some sense, so that any change, any difference in the illumination can be enhanced. And so, so the cameras, they have these sensors, right, and based on that, like when it gets the light from that object, so whenever like any light which is light which is slightly greater in luminosity which enters the sensors, so it gets enhanced, and in that sense like you can get a sort of a bright image in that sense. So and similarly, to this, you can have like a cell also working in that same fashion, but here the object is basically, what I say like is chemical in nature. Okay, so here it has to sense any slight change in the chemical the stimulus it has. So you can have a very dull profile, right? So this H stands for high and L stands for low. So the cell has this task to kind of sense this subtle difference in the intensity of this chemical signal. And so what it has is basically these, as I said, in the network side, this cascade, signaling cascade it has, which is basically a series of molecules where each molecule is activating the other molecule and that molecule activating the other molecule. So whenever any this so it gets the signal, so it kind of amplifies the signal in that some sense. And as I said, it has like this kind of an input-output profile, which is like similar to that of a like sensor, and it's able to kind of enhance any change which is there in the chemical stimulus, so that at the output, like it will have like a high contrast between the between the low and the high signal over here. So so this allows the cells to kind of make like right decisions, right? Because from the input side, it's very much not very clear like how much high and low are the signals are there. But when you have too much, like having sensitivity, high sensitivity is also not very good, okay, because in the environment that the cells they work in, it's very noisy, I mean in some sense. So your signal is always would be like corrupted with some noise in that sense. So when you like, and just compare it with photography, like when let's say you want to like take a picture, okay, which is in a very low light condition, but when your camera has like too much high sensitivity, then you can get this graininess in your picture, right? It's just because of that there is this, in the low light condition you have these the light signals that you are getting are very random in nature, and also the camera sensitive, the sensors are also kind of gets some way itself like gets corrupted. So, but also in a very, when it has very low sensitivity, then also like you will get a very dull kind of a picture in that some sense. So this is the same thing that happens in a cell. Okay, so when so cells like they get like a noisy signal which is from the output, okay, from the input, sorry, and also inside the cells, like because like these this interaction, the molecular interaction that is happening, these are like random in nature, okay, and this can induce noise into the system, and adding all these things, so basically like what would happen is that if you have too much high sensitivity, then the output that you will be getting, obviously it will have like a good contrast, like it will have like good contrast between the low and the high input, output, but the fact is that you can also get wrong signals, the spurious signals also, because this noise can drive your output to in a wrong regime in that sense. Right. So the question, that we are trying to ask over here, is that so basically the sensitivity, it depends on which the system that I am working on, the signaling cascade. It depends on the number of layers of interaction that the molecules have, right? So there can be 2 layers of interaction, okay. So once the signal is received from the input, so it gets passed on to, let's say, the one molecule, and that molecule then again interacts, like activates the other molecule. So there can be 2 layers of interaction can be there, and but this will be like not much sensitive. But then even you have like more layers, like when you have like, let's say, the down figure which you are seeing, let's say there are four layers are there. So there you can have like a very high sensitivity in the response. But the fact is that like but you have this noise also in this in your system. So that what would it do is that it will corrupt your signals. So basically when you have a high sensitivity, you're getting a sharp output, but your system, the output may not be accurate. Sometimes it may be accurate, sometimes it may not. But when you have like a low sensitivity, your the output is accurate, okay, but the response, the output that you are getting is very dull. It will not be very much magnified as such. So it will be difficult for the cells to kind of distinguish between what is the let's say a low signal and what is the high signal level. So the work that I'm trying to do over here is that trying to understand whether there is some trade-off is there or not, okay, between like let's say how accurate the signal, I mean the output can be, and also how much sensitivity is optimal for a cell to work with. Okay, yeah. So yes, that's it. Thank you.
Thanks, Soumyadeep. So if you have any questions, please you can ask. I don't see any. So thanks again. Sorry for this hiccup, but we really enjoyed your talk.
Okay, thank you.
Okay, so our next speaker is Prem Kumar, and he will tell us about approximate thermal state of a quantum system. Please, Prem.
Hi, so my name is Prem, and today I'm going to talk about, as sir said, about approximate thermal state of a quantum system. So I would like to thank Aden Stratton and Professor Subhashish Ghosh for helping with different aspects of this work, and recently it came in archive. So okay, so the question is, what is the problem? Many of you might be aware that the thermal state of a quantum system at inverse temperature beta, it is given as e to power minus beta of the Hamiltonian h, where this p square is the p is the momentum operator, p square by 2m is the kinetic term, plus Vx is the potential term. So the thermal state is just given by e to power minus beta of the Hamiltonian. But this is only true if the system is weakly interacting with its environment. The general thermal state can deviate from this state, and we know how to calculate that general state, but it's computationally very expensive, and general analytical expression for it is unknown. Its result for some limit is known actually. Recently in 2020, this PRL came, which says that in infinite coupling limit, the thermal state is given as e to power exponential of minus beta Vx. So the potential term is missing. Only Vx is there. So this result was there. So we are interested in finding out whether I mean can we find the given analytical expression for this thermal state in maybe more generalize this. To get into this, let me introduce you to path integral approach to quantum mechanics. So it's one of the simplest ways to introduce quantum mechanics to someone. The idea is that if you want to know what is the probability for a particle to go from one position to other position in some time, so what you do is you sum over the contribution of all the paths that the particle could have taken in that time. Each path will contribute something. In the end, you add all of this together, and this will give you the resulting contribution of the resulting probability of this transition to happen. Okay, so for open quantum system, same path integral gets slightly modified. I mean, it doesn't get modified, but the expression is given in this textbook, 30-year-old classic textbook. So basically the idea is that it looks complicated, but let me explain it to you. This let q tau be one of the paths that the particle could have taken. So sq tau is just a number, which let's forget how we will calculate for now, but let's say we have a computer program which can do it for us. So sq tau is just a number. What you do is you put it inside an exponential with a minus sign, e to the power minus sq tau, and this gives you the contribution of that path. And then you add over all the paths with their corresponding sq tau, and the sum end result gives you the final probability for that thing to happen. Okay, so let me get into the expression for sq tau. So it has basically three terms. The first and second term, some people who have studied path integral may be familiar with this first and second term. First term is just the kinetic term. Q tau by q dq by d tau is the velocity, so it's velocity square, mv square by 2, and the second term is a potential term plus vq. So the third term is coming because of the path, because of the environment, and this is let's forget what the expression for k tau minus tau prime is, but let's this is how it is. I'll not go in more detail. It's there in this textbook, but it's not required for our requirement. Okay. So the thing is, can we see this? So these people in this PRL, these people arrived at this result using perturbation theory. So the question is, can we see this directly from this equation, this infinite coupling result? The answer is yes, because this expression k, it's because of the environment. So if environment is not there, this k will be 0 and this third term will not be there. On the other hand, if the environment is there, strongly present there, then this factor k will be infinitely large. So this sq tau, so if for a path, if q tau minus q tau prime, tau and tau prime are at 2 different times. So if q tau minus q tau prime is positive or is non-zero, the square will be positive, it will multiply to a very large number, and this sq tau will become a very large number. When it goes inside an exponential with a minus sign, it becomes a very small number. So what this means is, for any path, if q tau and q tau prime are not the same, then that path will not contribute. So the only path that will contribute will look something like this, straight path, where q tau is equal to q tau prime for all tau prime, tau and tau prime. So the only straight path contributes in the large coupling limit. This would mean that the third term will not contribute at all for the paths which are contributing, because it will be large number multiplied by 0. And the first term will also not contribute, because dq tau of, because it's a straight path, this will also be 0. So kinetic term will also go, this dissipative path term will also go. The only term which will remain is this potential Vq. So this integral will become very trivial, and you will directly get this equation. I am not sure whether this argument is clear, but I mean, if you think about this, you will get that it becomes trivial in the infinite coupling limit, and we can directly see this result, ultra strong coupling result, coming directly from the path integral approach. So the question is, now that we have this intuitive way of looking at it, can we do better than this ultra strong coupling result? The answer is, I mean, if the coupling is infinite, then only one path contributes. If the coupling is not infinite, then only nearby paths will contribute. So we don't have to look for all the paths in the path integral, only nearby paths. And also, it turns out in the same textbook, the result, if the system was a harmonic oscillator, which is just a quadratic potential, if result was harmonic oscillator, the answer is analytically known. So if if the paths which are contributing have only like small variation, then you can locally approximate that potential as a harmonic oscillator. So what you basically do, you have, let's say, a complicated potential, everywhere you fit a harmonic oscillator, and you know the answer for harmonic oscillator, so you just cut and paste the answer there, and you get an analytical solution for the thermal state of that system. It will have some error, of course, but there will be some limits in which this result will be quite accurate. The limits are, of course, in high coupling limit, where this k diverges. Another limit is if Vq, the potential, is changing very slowly. So everywhere this harmonic approximation is quite a good approximation. No matter what be the distance on which the path integral is exploring the space, your harmonic approximation is doing a good job. So these are the two limits in which this approximation will work quite well. Okay, all well and good, but there is one problem. What about this inverted harmonic oscillator, this orange curve? So we are using a analytically known solution for an inverted harmonic oscillator to solve this problem. Will it even make sense, because the e to power minus beta h of an inverted harmonic oscillator is undefined? The answer is we can do that. The reason is it's undefined for some harmonic oscillator. If if the imaginary frequency of this harmonic oscillator is not too large, it turns out the state is undefined, but the local path integrals are still defined. The reason for this is this: the potential is inverted. The potential is inverted. So paths which have large deviation from this potential will tend to contribute more. But then in the path integral there are two terms, kinetic and dissipative terms, which will prevent the large deviation, paths with large deviation. This first term, kinetic and dissipative term, they will prevent the paths with large deviation to contribute more. So this kinetic and dissipative term versus this potential term. They have some kind of competition, and it turns out that the potential term only wins if its frequency is larger than some limit. So this approximation can work with by using, you can actually use the result for an inverted harmonic oscillator for this approximation as well. Okay, so these are the two limits in which this will work. Okay, and then I'll give you another limit in which this method will work exactly. So we talked about this dissipative term and this potential term. This dissipative terms in large coupling limit, it gives you exact result. This potential term also gives you a limit in which if your potential is changing slowly, then it will give you exact result. The first term also gives you a limit. That is the high temperature limit. In high temperature limit, the first term starts dominating, and any path which has any variation, that path will not contribute. The reason for this is like this. In this beta is inverse temperature. So in high temperature limit, beta goes to 0. So let's say I want to go from this part of the stage to that part and come back in 20 seconds. Then I'll need some energy to do that. But if I have to do the same thing in 1 second, or let's say 0.1 second, then I have to expend a lot of kinetic energy. This is the reason why the kinetic term dominates, and again the thermal state is given as e to power minus beta b. To summarize, this approximation works well in large coupling limit if potential is varying slowly, or if in the high temperature limit, or a mixture of these three. So okay, thank you.
Thanks, Prem, for this very nice talk and questions.
In the potential, you didn't fit the minima actually, but you fit it. So usually what you do, you fit the minima only.
No. I'm fitting at every point. This is just for illustration. At every point of this potential,
okay.
I'm putting a harmonic oscillator and using the answer for answer for harmonic oscillator at that point.
Okay. So this is only one of the possible.
Yeah, it's just for illustration.
Oh, okay. Thanks.
Any more questions?
For example, in the inverted harmonic oscillator case, you said you know the analytical solution.
Yes.
So can we do this for some cases when we don't know the analytical solutions or the potentials are not analytically solvable?
I mean, for harmonic oscillator, we know the analytical solution. We are using that to solve for unknown potential. But I didn't get your question.
In some of the cases, for example, in the inverted harmonic oscillator, when the path integral might not work that nicely.
So that's the thing. If we know how to solve the path integral even for inverted harmonic oscillator, if the imaginary frequency is not larger than some threshold. If it's larger than that threshold, it diverges. But for some inverted potential, again we can do the calculation. The thing is, if your potential has this sharp second derivative is very sharp, then for given coupling or temperature, it might not work. But again, in the infinite coupling or temperature limit, again the number of paths required are very small, and again this kicks in. So again this method in that limit is again applicable, because e to power minus beta Vx, what they arrived in this PRL, this is valid for any potential. So in the infinite coupling limit, it's always, even if it's any harmonic potential, it will work. I mean, if the potential itself, the actual potential is bounded, as long as it's bounded, this black curve, as long as this one is bounded, the harmonic approximation itself will work. So actually, okay, I don't know whether I answered your question.
Yeah, we can talk later. Thank you.
Okay.
Okay, thanks, Prem. And we end the first session by thanking all the speakers, and we will come at 11:40.